Hey there, Mr. Sutton back one more time for this radical chapter. In this one, we're going to close things out by solving radical equations. And the real-life payoff for this is we're going to figure out braking distance. For the warm-up on this one, pause the video and see if you can simplify these expressions in 30 seconds or less. You think you got it? All right, let's go through each one. Here we're asking for the thing I have to square to get x squared. Well, that would just be x. For this next one, I'm taking the thing I have to square to get x, that's what the square root of x is, and I'm squaring it. Well, when I take the thing I need to square to get x and I square it, I should get x. And same reasoning over here. This will be x plus 2, and this will be, x plus 2 again. So we're seeing a pattern here. The square and the square root undo each other. And we're going to use this relationship to solve radical equations in just a moment. Before we try to solve a radical equation, we should probably define what one is. It's not just any old equation that has a radical in there somewhere. A radical equation is an equation with a variable inside a radical. So, for example, 4 plus the square root of 15x plus 1 equals 0. The x is inside the radical, so this comes with special rules that we have to follow. But let's first start by getting the radical term all by itself. We can do that by subtracting the 4. And then how do we undo a square root? Why, with a square. But we have to square both sides. You can't just square one of them. So this negative 4 also gets squared. That gets rid of the radical on the left. So that's 15x plus 1 equals 16. And then we subtract the 1. That's 15. Divide by 15. And x equals 1. Or does it? So one thing we have to be careful about with radical equations is that you sometimes get what are called extraneous roots. These are really nasty. These are fake answers that, you did good algebra and got the answer here, but it's possible that when you plug this back in, it might not work in the original. And you might wonder, well, how can that possibly be the case? So let's actually go through now. You always have to check for extraneous roots with radical functions. In fact, you have to check for them with any function that has domain and range issues, like square roots that can't return or input negative numbers. Let's go ahead now and check this extraneous root by plugging it back into the original, and let's see what happens. By the way, this is a mandatory check. You can't just say, I'm just not going to check this time. I'll just hope that this works. You need to check and prove that this is a legit answer here. So we've got 15 times 1 is 15, plus 1 is 16. Square root of 16 is 4, and what is 4 plus 4? It's not 0. It's something else. It's 8. So we would say then that 1 is extraneous, which means it's not a good answer, so we have to cross it off. And if there were another answer, and that actually worked when we plugged it in, then that would be the answer. Since we've crossed off all the possible answers that we had here, we have to say there is no solution to this equation. Now, some of you, again, might be wondering how this can possibly happen. So let's consider an alternate reality here. This 4 that was negative that you squared and got the 16, if this had been a positive 4 that you had been squaring, you still would have gotten 16, wouldn't you? And you still would have gotten 1 for your final answer down here. If this had been a positive 4, well, this would have had to have been a negative 4 to start with. And if you had started with a negative 4 over here, then you would have been doing negative 4 plus positive 4. That would have given you the 0 that you so much wanted to match with that right side. So it's really the fact that we're squaring negatives and losing information that leads to these extraneous roots. Let's try another example. In this one, we've got radicals on both sides. Well, if squaring a radical on one side gets rid of it, squaring radicals on both sides should get rid of it. And hey, we have to square both sides of the equation anyway, right? So this just kills two birds with one stone. So that'll give us 7x plus 145 equals 2x plus 100. Now another way you can think about this, if the square root of something equals the square root of something else that looks different, those two somethings inside are going to have the same value in order for those two square roots to be the same value. Either way, let's go ahead and solve this. So that'll be, let's see, negative 45 on the right if we subtract, and 5x on the left. Divide by 5, we get x equals negative 9. Or does it? Let's plug back in and just be sure. So we've got 7 times 9 plus 145 square rooted, and 2 times negative 9 plus 100 square rooted. So that's negative 63 plus 145, which comes out to 82. And 2 times negative 9, that's negative 18 plus 100, also comes out to 82. Since those match, we have a good answer. And you might be thinking, well, I never need to check for extraneous roots on these because I'm not squaring negatives and losing information. You do still need to check for extraneous roots. Specifically on these kinds of problems, you're going to need to make sure you check inside the radical to see if you have negatives at the end. If whatever answer you get gives you a negative at the end of the problem inside a radical, then that's also another way to have an extraneous root that you have to throw out. Up to this point, we've only been dealing with square roots, but really the stuff we've been doing with radicals works with any kind of root, and since that last chapter on rational exponents, we know that there's more than just square roots now, like cube roots. Let's say you have the cube root of x minus 2 to the equals 3. Pause the video and see if you can figure out what to do in this situation. All right, let's see how you did. So if we want to undo a cube root, we need to cube it. A cube undoes a cube root. Fourth power undoes a fourth root. Really, whatever the root is here, you just use the same power to get rid of it. Don't forget to raise the right side to the third power as well. So this will be x minus 2 on the left side and 27 on the right. And then we just add 2 to get our answer of 29. And just to be on the safe side, you can check your answer on this one if you want. So 29 minus 2 is 27. Cube root of that is 3. So 3 equals 3. It turns out you don't actually have to check your answer in the same zealous fashion with odd roots. Odd roots don't have any domain or range issues. They actually are all real numbers in every direction, but it never hurts to be on the safe side and double check it anyway. We're going to wrap this one up with a real-life application. So the highest speed, which we'll call v for velocity, at which you can drive and still brake before d feet, is given by v equals the square root of 20 times d. So if you want to know the highest speed that you can brake at a certain distance, multiply the distance by 20 and square root it. To the nearest foot, what is the braking distance at the highway speed limit of 40 miles per hour? So we don't hit the deer here. So to figure this out, if we're trying to get the distance, we need to plug the 40 in for the v. So we can say 40 equals the square root of 20d. And go ahead now and solve this one on your own. Did you square both sides? Hope you did. That's 1600 equals 20d. Dividing by 20, that's going to be 80. So 80 feet is our braking distance. Just to be on the safe side, let's double check that and plug it in. So 20 times 80, that is 1600. Square root of that is indeed 40. So that's all for now. Until next time, this is Mr. Sutton signing off. Goodbye, crazy bug-eyed deer.